Okay, that got awkward fast. Okay, here we go. So as the system approaches equilibrium, here's a picture of equilibrium, by the way. Can you see, like, I don't know if you see very well, but one's blue, one's purple. Yeah. So right here, that's where they'd be battling between, oh, I'm going to be purple. No, I'm going to be blue. Well, I'm going to go back to purple. No, I'm going to be blue. But it's not going up and down, right? There's definitely an interchange here, but the forward and reverse are happening at the same rate. I think I kind of disturbed that. I don't know. Does it look the same? But then, if I stir that, it will end up one of those two colors. But I don't want to stir it because I'm using it for my other classes as well. No, it stays stirred forever. Sorry. What is it? That's acid on one level and base on another level. Okay, so here we go. When this first starts, this is our rate. Now the rate graph is different than the height of the reactants, because that'd be the concentration. But these will come together. In this graph, the rates become equal. But this is not the same graph we were drawing before. Oh, I just erased it, I think. This, yeah, I am now. This is showing you concentration versus time. This is showing you rate versus time. Those are two different things. At equilibrium, the rates become equal. All right, at equilibrium, the concentrations don't change. They're not required to be equal. They just can't change anymore because the rates are constant. If I make $20 every single hour I'm awake, but I spend $20 every minute or every, not minute, hour I'm awake, I have really no change in how much money I have. I have a drinking problem. 20 refills an hour. Just kidding. All right, next. Here we go. This was the big long definition. At equilibrium, the forward and reverse reactions are proceeding at the same rate. Next, once equilibrium is achieved, the amount of each reactant and product remains constant. And kind of so far easy ideas to think about. Well, there's math. When we get to math, though, don't panic about it. Math is essentially a ratio between the concentration of the products over the reactants. So if we were just, obviously I've done this before, where these dashes are, if this was like a 15 and this was an 8, we would take our products, which is 15 over 8, and we'd come up with a number that I shouldn't have chosen. 1.875, I think, but whatever. That's all you do. Now, it's going to seem way more complicated. I am really an impressive human being.
That was really, I like. That's spot on.
I'm really good at math. / I cheat.
How do you cheat?
Because it's just an 1/8 off, and that's 0.125.
Oh yeah, that's true.
It's cheating knowing that. How dare my teachers teach me that crap? So, all right, now, this is a really important thing. You see this right here. We are going to talk about this math, and it's called K. But, oh, there's so many Ks in your future. So I don't get to choose. K means constant. But I know, it just gets worse.
Oh yeah, it's K for constant.
Now, please, I'm about to fast forward into some slides where we're going to talk about K. Everyone look at your partner. K in chapter 15 is not the same as K in chapter 14. Say it. They're German constants. Okay. Are we ready? So the math, please, with me. The math, where we compare the products over the reactant concentration, we call that K. please stop talking. Then I'll validate that you're listening to me and feel better about myself. Okay. This is called the KEQ or KC. No, you don't write it. You'll do it so many times. It's like writing the number 2. You're like, oh, 2. Oh, well, I don't have to write that anymore. I used it a billion times. KEQ stands for the equilibrium constant. KC means the equilibrium constant, where you use concentration. K is just a plain K in chapter 14, and we call it the rate constant. Now, let's see if the next slide blows up the Ks. Nope. Here you go. Here's your warning. We have K, and that's with rates. That doesn't look like a T. Someone say my name? Yeah. Oh, I said, did someone say my name? Danny? Okay. That's chapter 14.
That was the most awkward thing I've ever done.
Yeah. I've never felt better about our friendship, though. Okay. Don't write this down.
Oh.
Don't.
Why would you do this?
You should have showed this after the trimester once we started third try.
All right.
Are we using all of them?
We'll learn all of them. Now, shush, shush, shush. Don't make that face. Look. Look. They're all the same math. Everyone shut up. They're all the same math. That's the good thing. We're going to learn 7 things in the next 3 chapters that all have the same math. Now look. KEQ is the general, just saying we're finding this ratio. Typically it's with concentration, but specifically K when we have concentrations. K when we use pressure. K when we're finding it for an acid. K when we're finding it for a base. K, that's a B. My bad, my lad. KW, that's a constant for water. It's the same number every time. And Ka times Kb equals Kw. So if you have one, you have the other. Boom. And KSP, that's the easiest of all of them. That means the solubility product. What? There should be a K. Tom is amazing, but there isn't. Oh, yeah. K, W, K, A, K, B. Drawn to scale. Okay, here we go. Thank you. Here we go. Okay, depicting equilibrium. In a system at equilibrium, both the forward and reverse reactions are being carried out as a result. We write its equation with a double arrow. So we have N2O4 gas going to 2NO2 or being formed from 2NO2 making N2O4. Okay, we haven't done a double arrow yet, right?
We looked at one time.
Okay, so all it means is this reaction will go one way depending on what the, like, I almost said settings, what the conditions are, that's the word I'm looking for, or the other, like it can go both directions. Okay, now this is where I've gone off before, the equilibrium constant. And look, what did I say earlier? It's all the same math. So it seems like, man, I'm going to transfer. No, it's the same math equation. Here we go. Now, this is how we come up with this stuff. Don't write any of this down. So here we go. We're just going to jump into this. The forward reaction is this, and the rate law would be that. And this is a K rate, K. But don't worry about it. It would be equal to this. This F should be lowercase, and it means forward. So the rate law would be rate, K for forward, concentration of N2O4 raised to the first. Okay, now you don't need to know about it. I'm just telling you that. What would the reverse then be? KR would be NO2 squared. You okay with that? Now, chill. Doing some algebra. Therefore, at equilibrium, rate forward equals rate reverse, Kf, who cares? Rewriting this becomes that, where we have the concentration of NO2 squared over N2O4. Now, this 2, any idea where it came from? Okay, so it's not, this isn't something we got to find in a table. This isn't something we got to put in my calculator. It's the coefficient. America. Okay, now rewriting it, it becomes this, and there we go. We call, sure, I never, yep, you're welcome. So instead of writing this, oh my laws, Thomas Davidson. Instead of writing Kf over Kr, which is what it is, we call that just K, knowing that it's how I came up with rate laws that show me this ratio at equilibrium. Now, there was a ton of stuff in there I didn't bother to touch. I don't care. It's like when they're like, okay, we're going to prove the Pythagorean theorem. You're like, I'm going to go to sleep for 10 minutes because I know the Pythagorean theorem. I don't care how he came up with it. All right, it works. Okay, so our equilibrium expression or constant is the concentration of the products raised to their coefficient divided by the concentration of their reactants raised to its coefficient. Now we can certainly have more things in here. It's gonna be fine. Okay, I want you to put something in your notes. This is a pet peeve from my very first year. This thing also has another name, and I don't like it, but it has another name. This is also called the mass action expression. And it's the same stuff. The mass action expression is the same thing as K. Now, why? I don't know. But the reason why it's a pet peeve, you know, it's my first year teaching. I don't even really know what I'm doing. Okay, whatever. We cover it. The kids come back the next day and they're like, you never taught us about the mass action expression, which was its equilibrium. It's like the most important part of the whole test. And like half of them failed because they didn't even know how to do the first problem because I never taught them that equilibrium expression and mass action expression are the same thing. Okay. Whatever you said is probably true. I didn't understand you though. I'm going down. Yes. Is that a question? That's how I just communicate with my wife now. Like, yes?
That's crazy.
The answer is always say yes.
That is crazy. Okay, so mass action expression, you got it. Here we go. To generalize this expression, this may not help, but if you have AA plus BB goes to CC plus DD, where the small ones are the coefficients and the large ones are the formulas, you end up with C to the C, D to the D divided by AABB. Can you, is that all right? It really is a fairly easy concept for most kids. And hey, look, I warned them last year. This thing's also called the mass action expression. I'm still bitter. It was me. It was me. Like I had to take accountability for them failing their AP test. Luckily, I didn't pay, so just kidding. Okay. Is anyone writing that down? Like, do you want me to stay longer? Okay, here we go. Now, you don't need to do all 10 of these. Pick one of these and write the equilibrium expression. Take one of them. I'll do number one. K is equal to the concentration of Al raised to some number that I have to balance, and O2 raised to some number that I would get by balancing, divided by the Al2O3 raised to some number that I would have to balance. That's it. So you would have to balance it and then write the expression. What? Whatever one you pick, I'll do this one. Oh, I see a 3 and 2. Whoops, I screwed it up. There we go. So then these would be a 3. This would be a 2, and that would be a 4. That would be the mass action expression or equilibrium expression for that reaction. Wow. Now, every day I get a text about one of my children not going to seminary. Carly. Just kidding. I'll give you a hint. They're a senior.
Oh, that's a surprise.
Hmm.
Seniors always go to their classes.
I know, it's weird. Right? Yeah. Okay, we done? Raise your hands if you're done. 1, 2, 3, 4, 5. Good. Redheads in the back, repping. All right, good. Not redheads in the back. Redheads towards the back. Good. Okay, I'm going to tell you something real quick. You may be annoyed. None of these are what you just wrote.
I'm gonna cry.
Don't. See this right here? No. For now, ignore the state that the species is in.
So everything we just did is a lie.
No, sort of. Look at the screen. The equilibrium expression for this one, KEQ for this top one, would actually have been KEQ equals O2 cubed, and that would be it. And we're going to go over a slide in a minute. Just stick with me. It's all right. No, you're not. When we did all the Ks, we said K when there is concentration, right? K when there's pressure, K with an acid, K with a base, K with water, K solubility product, and I probably missed another one. But look, in this equation, you're taking a solid piece of aluminum oxide and you're heating it and you get a solid piece of aluminum and oxygen gas. Is there really a concentration of Al and Al2O3? It's not in a solution. So we technically, and we'll go on a slide very soon, when you write these, we don't typically include, well, we never do, I shouldn't say typically, we would not include a solid. So this one would be a gas, so it's the only one that would actually have an equilibrium expression.
So do we only treat like gases?
Gases and aqueous, yeah, don't say liquids.
Because you can't have a concentration
Of water.
of water. How
Yep.
does that water?
Yep. So anyway, like we're going to get there. Don't stress. It makes it easier. So there's your chapter breakdown. KC, KP, KA, KB, KW, KSP. No,
I already feel a little confused. So
it's all right. I'll bring you back. All right. So, K, I'm sorry, the equilibrium constant. Because pressure is proportional to concentration for gases in a closed system, the equilibrium expression can also be written Kp, where we use the pressure of C raised to C times the pressure of D raised to D.
like we're gonna have to do pump nerd with this
Who doesn't like PivNerd? Transfer out. No, there's not really much PivNerd here. There is not. It just gives it to you. So don't worry about that. But we're just saying, hey, we can have it with concentrations. We can also have it with pressures. That's all you got to know. Okay. So
Yeah, that's what I did.
here was an example. We have two. This my slate gave up on me. 2 Ag plus what was it reacting with? 1. Okay, so I thought you said silver. Like he fails. That's silver. Goes to Ag2S. Now, we're going to pretend that these are all in concentrations. You with me? We'll pretend they all are. And I'm going to tell you that at equilibrium, I have 0.3, I have 0.1, and I have 0.2. Now, if you're like, that doesn't make sense with the balance things, those don't matter. They tell us the change, but they don't tell us what we have at the end, okay? So what we want to know is the KEQ, or the mass action answer, the literal number. So what we would do is we would first write out the concentration of the products and raise them to their coefficient. So S was raised to the first, Ag2S was raised to the first. With me? Oh, the arrow's here. Sorry, thank you. I was sorry. Okay, there you go. I apologize. So Ag2S to the first is the only product. I apologize about that. And then we'll divide it now by Ag to the second and S to the first. You with me? So now I just plug it in. So I'll do this one in blue. What is the concentration of Ag2S? 0.2 to the first over Ag squared. So I have 0.3 squared and S. Whoops, I'm an idiot sometimes. I'm so stupid. And S is 0.1 to the first. And I just type it in carefully. We always put the whole denominator in parentheses. Should I do it, Tom? Should I tell him? It's not honesty. It's a calculator trick I've used my entire life. Okay. If this confuses you, never consider it again. And I might have already told you this. So I do everything wrong in my calculator. This only listen if you think you have, if you're smarter than me. So you should all listen. I don't like putting parentheses in crap. Like I can now. I have a TI-84, but back in the day I didn't. So I would 0.3, I would square it, and I'd multiply it by 0.1, and I would divide it by 0.2. And then I hit the 1 over X button, because that's upside down, is it not, the way I did it? But that way I can do all the steps, and then I just hit 1 over X, and that tells me my answer. Now, if that confused you, then don't ever do it. But I do it a ton. I still do it, and I don't do math very often. Yeah, but remember, I'm TOM 46, and TI-84s didn't exist 25 years ago.
1 over X.
Yeah, same thing.
Okay, I was looking for the button.
Yeah, sorry. It's X to the -1. It just, all it does is it takes your fraction and flips it. And I did it all backwards, so I have the wrong answer. I need to flip it.
Below the green button.
I feel like I've ruined your lives.
So with equilibrium, could it go the other way as well?
Yeah, if it asks us for K of the reverse, we could do it. But we'll typically do it just from
Should
left
it
to
be the
right.
same numbers?
No, it would be 1 over. And we're going to learn that on a slide. Okay, what did we end up here? I have no idea.
22.2 repeating.
Why didn't we do this a couple days ago? Okay, now my friends, K has no unit. We call this a unitless number.
I didn't know there were numbers like
Don't put a unit on it. Because I mean, technically it would be per mole squared or molarity squared. It's fine, but it's just a ratio. We don't really worry about putting a unit for K. Well, first off, raise your hands if you were okay with doing what we just did. You have the equation, you have to balance it. You have to figure out the expression and then just substitute. It's always products over reactants. If you haven't written that, definitely do. It's always the products over the reactants. And the reason why is because when they came up with this, they said that's what we're going to do. Because they could have done it the other way around. Because this is just a random number we're talking. Like, it helps us understand like which way a reaction is going to go. We're going to learn that. But we could have done it the other way. They just said products over reactants.
So with once they go both ways, does it matter?
It does. And Tim asked this question a second ago. He said, what if it went the other way? If it goes the other way, the answer is 1 over that answer. It'd be 1 over 22.2. Because what it would do, if we did it for the reverse reaction, these would now be the products, and that would have been the reactant. And so it's everything upside down. And that's a slide coming up. It might be coming like right now. Oh, no, it's an example. All right. Did someone say they hate this?
No, I was thinking, no, it's the Heber process.
Have we read about this before? Learned about it? Okay. The textbook, which you no longer use, loves the Haber process. And you should too, because we might not be alive without it. The Haber process was discovered by like Franz Haber or something like that to produce NH3. Does anyone know what that does for our life? No. No. It doesn't technically do anything for inside my body. It's fertilizer. It's ammonia-based fertilizers, which took crop yields, which this isn't a farming class, but like that many things per acre or whatever, and made it crazy higher by adding ammonia. Now, how it works, I don't even know. I don't even care. I just know that our planet has X amount of people that it can feed. And this process made X go way higher. Because I really believe we'd be out of food by now if we didn't have modern agriculture and fertilizer and all that. Like, this planet would have maxed out. We would have all started killing each other a long time ago. Well, maybe, but okay, so here we go. Anyway, this dude came up with this, and K is really important here. So let's practice it. Calculate KEQ for the above reaction if the equilibrium concentrations were, and they're written above it. So do that as quick as you can. You have to balance it. Oh, wouldn't that be nice? Are you done? I feel like you're not done. How's it going?
We're good. I'm just
Sorry, I stayed over here.
Physics final.
How's that class been?
It's been pretty good.
Good.
Like, he does practice quizzes like he used to do. So I'm like, that's
You're
super
welcome.
helpful. I know. I was like, they're so helpful.
Good.
So I'm just like trying to take them as many times as I can. You know?
Good. I've tried to turn my department into clones of me
Yeah.
because it makes things easy.
Oh yeah. Absolutely. Like, I wish like all the teachers teaching style.
Well, they all think I'm too easy is the problem, which I probably am. Not in AP though. Whoops. Is that what you got?
That's a big one.
Hey, K is allowed to be huge and really small. Don't panic either way. You're like, I got 10.8 million. You're like, well, that's fine. Or 0.0001. That's fine. Whoops, there's not a. This should be a pretty big number, right? Is it 5,000? Oh, okay. Somewhere in our life is a 5,000. I know there's one coming. Might be on the test. Where? Well, there's one where the answer is just plain 5,000. And kids are always like, can it really be that whole number? Yeah, you can. I have no problem with that. Because it says it on your calculator.
Scientific notation is sweet.
Okay, thumbs up if you're okay with that.
I want to be a scientist.
Is there anyone willing to admit they don't know how to use their calculator very well? Okay, be careful on the calculators because I will see this. I will see it on your test paper, and then this is like 6. I'm like, oh, my babies, you had it. Who was that? I wrote a note on your test, like check your math. I don't know what you did wrong. She did every single thing right and had a wrong number on their answer. So it was kind of a bummer. Okay, this so far hopefully feels like a nice, easy stroll. Chapter 15 does not get much harder. It gets a tiny bit, but not much harder. So hopefully you feel all right about that. All right. Oh, what's this cute thing? It said not bad, and I turned it into a beautiful human. It was a picture of my wife. What?
That was recorded. That was going to be.
All right. You'll see this question again sometime. Ooh. All right, I'm going to stop this.